Good morning. Good morning. Good morning. Okay. Let's. All right. Let's go ahead and continue on here. So we did questions 1 and 2. Are wanting to look now at questions 3 and 4. So they're both very similar. This whole packet's kind of more about like differential equations and things like that. Also, for most of these, for all these questions, most all of these questions on this packet, we have no particular need for a calculator. Okay, which is more along the lines of what you'll see, or it is what you'll see if you're taking the AP test. In that, they said that everything will be able to be done without a calculator. You're still allowed to use a calculator, but they've indicated that anything that we need to do could just be done with a 4-function calculator, or maybe not even needed to use that. So probably more an emphasis on equations of things and variables and justification of ideas rather than just specifically do this calculation. Right. So number 3, consider the differential equation dy dx equals 2x minus y. Part A, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. All right, so slope field is something we talked about. Basically what this just means is at each point, what does the slope look like? Well, we have an equation for dy dx, which is the derivative is a slope, basically. Okay, so we just have to plug in these various points and figure out what the slope would be. All right, so for example, at the point, this would be 0, 2, right? That point. So if I plug that into this equation, right, 0 is the x value, 2 is the y value. So 2 times 0 is 0, 0 minus 2. So a slope of negative 2. So probably something like this. Let's go down to this point, 0, 1. All right, 2 times 0 is 0, minus 1. So a little more shallow, right? But still a negative slope. Let's come down here. 0, negative 1. So 2 times 0 is 0, minus negative 1. So that makes a slope of positive 1. So kind of the same angle as up here, but just going in the opposite direction now because it's a positive slope. Moving over. 1, negative 1. All right, so now I have an actual x value that's not just 0. So 2 times 1 is 2, minus negative 1. So that's positive 3. So this should be pretty steep. right? Steeper than this one because this slope up here that we did was -2. So a slope of +3. So obviously it's going in the other direction because it's a positive slope, but it should be steeper as well. Right. Over here, 1, 1. 2 times 1 is 2. -1 is 1. So just a positive slope of 1. And then up here at 1, 2. 2 times 1 is 2. 2 minus 2 is 0. All right, slope of 0 is just a horizontal line. I can't draw a line through that dot. We'll say that works. I can't do it. So there's my slope field. It says to do it for these 6 points specifically. So there's those 6 points specifically. Part B, find the second derivative in terms of x and y. Determine the concavity of all solution curves for the given differential equations in quadrant 2. Give a reason for your answer. All right. So part B. So first I want the second derivative. Now I already know the first derivative, dy dx, is 2x minus y. Okay, so if I want to take the derivative again, notice, and we talked about this last time, or reviewed this last time, that that numerator dy, but I have an actual y on the right side of the equation. So if I take that derivative, it's not just a normal derivative. So derivative of 2x, yeah, this is with respect to x, right? That dx in the denominator. So that's just a normal derivative. So derivative of 2x is 2. Minus, all right, the derivative of y. If I just think about y as a variable that I'm taking the derivative of, that derivative would be 1. But since we're not differentiating with respect to y, then we have to use our chain rule. And so our derivative is 1 times dy dx. But we already know what dy dx is. So we can plug that in. 2 minus 2x minus y. So 2 minus 2x plus y. Okay, so that's the second derivative, which is part of the answer. That's not all it wanted, though. Determine the concavity in quadrant 2. Oops. Okay, so in quadrant 2, let me think about what I know about the values of quadrant 2. So quadrant 2 is over here, right? So for example, I know that all the x values will be negative and all the y values will be negative for quadrant 2. Okay, so let me see if I can use that to determine information about this second derivative, right? Because the question asks concavity, but concavity I know is related to the second derivative. Positive second derivative means concave up, negative second derivative means concave down. Okay, so I made a mistake over here. All right, x is, for quadrant 2, x is less than 0. I'm on the left side of the x-axis, but y is a positive number, right? This is still above the x-axis, so these y values would be positive. So x is negative, y is positive. Okay, so 2 minus 2 times x. Well, if x is a negative number, which is then being multiplied by -2, then that means I know that this will always be positive in quadrant 2. Right, so actually this is like 2 plus some positive number. Okay, well 2 plus a positive number is going to stay positive. And then plus y, but we also know that y is positive. So all 3 of these terms will be positive. Okay, which means that this second derivative is always going to be positive in quadrant 2. Right, therefore, if the second derivative is always positive, how does that relate to the concavity? So that means, how did they word this? Concavity of all solution curves. Okay. So let's say all solution curves will be concave up in quadrant 2. How do we know that? Because since x is less than 0 and y is greater than 0 in quadrant 2, then the second derivative is positive in quadrant 2. All right, so we gave an explanation, we gave a reason for why. We knew we figured out by using the second derivative. Part 3, or not part 3, part C, or B. What are we doing? Part C. Let y equals f of x be the particular solution to the differential equation with initial condition f of 2 equals 3. Does f have a relative minimum, maximum, or neither at x equals 2? Justify your answer. Okay. So let's think about first, what do we know about... So we have this initial condition, but in terms of a relative minimum or a relative maximum, what do we know has to be true? So if there's a relative min at, there's a relative min or max at, let's say, x equals a, some number, well, then the thing that we know must be true is that the derivative at that number is 0. Remember, because relative max and mins always happen whenever that derivative is 0. Right? That slope of the tangent line is 0. Okay. So if this question is asking us specifically what is happening at x equals 2, so what I'm basically asking then is f prime of 2 equal to 0? Right, this is what we don't know. We know that f of 2 is 3. Wait, is that what it told us? F of 2, yeah, f of 2 is 3. But what about, in order for that to be a relative min or a relative max, the derivative of f at 2 would need to be 0 for sure. All right. Well, we already have an equation for the derivative, right? We already have dy dx. Okay, so let's just see what happens. Dy dx at, so if x is 2, that means y is 3, right? We know that from the initial condition. If x is 2, if we plug in 2 to the f, the original function, or the, I guess not the original. The original we were given is dy dx, but just the regular function f, if we plug in 2, we get 3. All right, so the formula is 2x minus y. Okay, so 2 times 2 minus 3. which is 1. And more importantly than it being 1 is that this is not 0. Right? So we know that if it were to be a relative min or max, it has to be the case that the derivative at that spot is 0. But it's not. Okay, so we can just automatically say, right, f has neither a relative min nor a relative max at x equals 2. And I think it tells us to justify. Yeah, justify your answer. So that's fine. Oh, can I get red? How do I know that? Since f prime of 2 equals 1, which is not 0. Okay. Part D. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. Okay. So values of the constants m and b for which y is a solution to the differential equation. All right, so we're saying, let's assume we have an original, a solution y equals mx plus b, that if I take the derivative of this equation, I'm going to get this. So the question is, what values do I plug in for m and what do I plug in for b that would make it true that that derivative equals this? Okay. Cool. So let's do that. Let's go part D. So I'm going to start off with y equals mx plus b. Right? If I take the derivative of both sides, so derivative of y dy dx, derivative of the right side, if I take the derivative of mx plus b, I'm just going to get m. Right? And this should make sense to us because m we know represents a slope. So yeah, the derivative is the slope. That's like the same thing. This makes sense so far. Okay, but we also know from our original equation that dy dx is the same thing as 2x minus y. That's what the problem was given to us at the beginning. So let me take this and set them equal to each other. So 2x minus y equals m. Okay, but now that I have an equation 2x minus y equals m, well, I also know y is the same thing as mx plus b. Right? So let me go through and substitute that into this equation. So 2x I guess you guys might not be able to see. Move that down. Okay, so if you couldn't see, so I was just saying this was our original equation over here that was given to us for dy dx. Over here I just took the derivative of y equals mx plus b, so I get dy dx equals m. Well, I have two equations now for dy dx, so why don't I just set those equal to each other? 2x minus y equals m. And now what I'm doing is I'm going through and substituting for y mx plus b. All right. Let's see. I'm gonna distribute this minus sign, and I'm also gonna bring my m over to the left side. So 2x minus mx minus b minus m. And I'm just gonna, so kind of like what we did for partial fractions, I'm gonna try to solve these by kind of grouping some stuff together. So like for instance, both these terms have an x in them. So I'm gonna factor out that x, so I get 2 minus m x. Oops, I guess on the right side I would have equals 0. Minus b minus m, both those have a negative. I could factor that out. Minus b plus m. Or I could leave it in there. I could say plus minus b minus m. Yeah, either way. Okay. So equals 0 on the right. So really what I have here is just like kind of like when we did partial fraction decomposition. If I imagine that the parts all have to match up, so like the x, whatever the coefficient of x is on the left side has to be whatever the coefficient of x is on the right side. But in this case, we don't have anything on the right side, but that's fine. We can still think about that as like 0x plus 0. Right? This is a really fancy, drawn out way of just writing 0. But what it means is that this should be equal to this. So it should be that 2 minus m equals 0. Therefore, m equals 2. And it should be that minus b plus m is the same thing as 0 as well. So b plus m equals 0. Therefore, b equals negative m. But I already know what m is. M is 2. So that means b is negative 2. Right? And this is exactly what we were trying to solve for. The question asks us what m and what b would we need in order to make this a particular solution. So we just kind of had to work our way backwards, mostly just doing a lot of substitution. Right, setting and solving so that we could solve for m and b. Right, we basically ended up making it a system of equations. I don't know if we had to justify or anything, but let's check. Nope, just find the values. Okay, great. So we're done. We found the values. M is 2, b is negative 2. Okay. Number 4. Consider the differential equation dy dx equals x squared minus 1/2 y. All right. A, find the second derivative. Okay, so this question is very similar. So first, let me start with dy dx, x squared minus 1/2 y. Okay. All right, so I'm having to do implicit differentiation. So if I want to get to the second derivative, so derivative of the left side, great, just becomes d squared y over dx squared. Equals, so this is a derivative with respect to x, so we can just do that one normal, 2x, minus 1/2 y, so minus 1/2, but chain rule, we need dy dx there. And dy dx, we already know what that is. We have an equation for that, so we can go ahead and just plug that in. Okay. So there we go. There's our second derivative. That's all that part A asked for, is just find the second derivative. In terms of x and y, yep, that makes sense, because over here on the right side, we just have x's and y's, you know, coefficients, but no other variables besides x and y. Okay, part B. Let y equals f of x be the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph have a relative minimum, relative maximum, or neither at the point -2, 8? Okay, so very similar to what we talked about on our last problem as well. Okay, for part B, in order to be a relative min or max, basically what we need to figure out then is the derivative at 2, right? Because it's at the x value, so, or sorry, at -2, my fault. Is that derivative at -2 equal to 0? Right? If it is, then we could then move on to determine if it's a relative min or max. If it's not, then we could say it's neither, right? So, but we already have an equation for the derivative. We know that dy dx is what was originally given to us. So now we're just evaluating dy dx at -2, 8. X squared minus 1/2 y. Okay, so x squared, so -2 squared minus 1/2 times 8. Yes. Okay, so 4 minus 4 is 0. Okay. So it does turn out that it is going to be a relative min or max. Now, we're not done there, though. This is a little bit different. So last time we got a number that wasn't 0, we could just automatically say, no, it's not a relative min or max. For this problem, we do get 0 for the derivative at that point. So now we need to distinguish, is this a relative minimum or is this a relative maximum? Okay, and the way to do that, the way that we specifically determine is it a relative min or max, is we want to consider the second derivative. Oops. What am I writing? And we want to evaluate that at -2, 8. Right? Because remember, if we already know that the derivative is 0, well, then now we just need to figure out what is the concavity. Is it concave up or concave down? Because it's either one of these options. So at this point, the derivative is 0. And at this point, the derivative is 0. But depending on if it's concave up or concave down, we'll have a relative min or a relative max, right? Here we got a relative max. Here we've got a relative min. Okay, so we definitely know it's one of them because that derivative, that first derivative is 0. But now let's figure out the second derivative so we can determine the concavity, because that will help us determine specifically if it's a relative min or relative max. All right, the second derivative formula was much longer. What was it? Oh gosh, I'm never going to remember that. 2x minus 1/2 x squared minus 1/2 y. 2x, so 2 times negative 2 minus 1/2 times x squared minus 1/2 times y. Is that right? Two x minus 1/2 x squared minus 1/2 y. Okay, yeah. I just have to. I have to flip back and forth between pages or scroll up and down. Okay, so let's just calculate this. -4. This 1/2. -2 squared is +4. 4 minus 4 is 0. Okay, great. -1/2 times 0. Okay, great. So this is just -4. Now that's important because that tells us it's negative. So it's concave down. So if it's concave down and we have this critical point, we know then this is a relative max. So let's write that out. The graph of f has a relative max at the point -2, +8. I'm sure it asked us for justification. Yes, justify your answer. Okay. So let's just kind of summarize the information that we solved for and figured out. Right. So since the first derivative is 0 and the second derivative is negative. Right. If you remember, this is the second derivative test. Right. This is just using. So we use the first derivative just to identify the critical points. Well, then, is it an actual max or min? Well, we use the second derivative to confirm one or the other. Right. So we could also say, by the second derivative test. That would probably be acceptable as well. All right, and part C. Oh, there's 2 more parts. Let y equals g of x be the particular solution. G of -1 equals 2. I'm sure that will be important. Find the limit of this show work. Okay. I need to take an hour to study this limit so that when I go to the next 2 pages, I can remember what the heck it says. G of x minus 2, 3x plus 1 squared. Okay, let's try it. So the limit as x approaches -1, g of x minus 2 over, 3 times x plus 1 squared. I think that's right. And we know from our initial conditions that g of -1 equals 2, I believe. Yes. Yeah, okay, great. All right, so anytime we're asked, I can barely remember. It's tough, man. It's tough out here. Anytime we're asked to solve a limit, our first attempt at solving it should just be plug in the number and see what happens. So in the numerator, g of -1 Well, we know from our initial condition over here, g of negative 1 equals 2. So 2 minus 2, all right, 0 in the numerator. Denominator, negative 1 plus 1 is 0. 0 squared, 0. 0 times 3 is 0. Okay, so I have 0 over 0. Which is an indeterminate form. Which tells me I can use L'Hopital's rule, and maybe that'll help me out. So we're going to take the derivative. So the denominator, this will just be a chain rule. So first, the outer function is the power rule. So 2 times 3 is 6. X plus 1. 2 minus 1 is 1. So I don't really need to put that exponent up to the first power there. Chain rule times the derivative of the inside, but the derivative of x plus 1 is just 1. So that's just times 1. I don't need to write it. But the numerator, so g prime, or wait, I don't want to plug in negative 1 yet. All right, for the numerator, the derivative of g is just g prime. Minus 2, the derivative would be 0. So we just have g prime of x in the numerator. The denominator is 6 times x plus 1. Okay, equals, so let's try it now. Let's try plugging in negative 1 now. Well, in the denominator, negative 1 plus 1 is still 0. So 0 times 6 is also still 0. So I don't like this yet, but remember, we can only use L'Hopital's rule if we get 0 over 0 or infinity over infinity. So just because there's a 0 in the denominator does not mean we just automatically can use L'Hopital's rule. Okay, so let's go back. We need to know, what is g prime of negative 1? Well, remember, g is just a solution to this. So this is, my derivative is g prime. Okay, so if I evaluate this dy dx at x equals negative 1, but look, I need a y value as well, but that's fine because the initial problem tells me for g, if the x value is negative 1, the y value is 2. So I'm evaluating this at negative 1, positive 2. So that would be 1 half times 2 is 1, so 1 minus 1, 0. So it is true, I do get 0 over 0. All right, and I'll go back to that. That was kind of quick. So again, g, just normal g, is a solution to this differential equation. So if I take the derivative of g, it's going to get me right back here. Now I want to know what happens when I plug in negative 1. But since this is a differential equation that needs x and y, I know from the initial conditions, if x is negative 1, y is 2. So that's why I plugged in negative 1 for x and positive 2 for y. Okay. But we got 0 over 0 again, so let's again use L'Hopital's rule. So the derivative of g prime is g double prime. 6 times x plus 1. That derivative would just be 6. Right, if you need to think about this distributed, 6x plus 6, yeah, that derivative is just 6. Okay, so I'm definitely at least not going to get 0 or infinity in the denominator. So at the very least, I'm just done using L'Hopital's rule. I can't do it anymore, definitely, because I just have a 6 down there. But now, g double prime of -1 is what? Well, remember, g prime is dy dx, so g double prime is just the second derivative. Well, we already had a formula for that, right? We did that. That was our part A. Right, this thing, 2x, oh gosh, the other thing I can't remember. All right, so let me solve that off to the side here. All right, evaluated at x equals -1, y equals 2, right? That's from the initial conditions. So 2x, so 2 times -1 minus 1/2. X squared, so -1 squared is 1 minus 1/2 times 2, which is also 1. Okay, so that's all 0. So this just equals -2. So -2/6, -1/3. So a lot of just keeping track of the correct equations in this one, and recognizing, you know, when it says g prime, well, that's really just asking me for dy dx, or g double prime, that's just the second derivative that we calculated from part A. And I don't think it just was the limit. I don't think we needed any kind of more justification. Yeah, it just says show the work. So we showed the work. We're good. All right, lastly, part D. Let y be the particular solution to the given differential equation with h of 0 equals 2. Use Euler's method. All right, Euler's method again. Starting at x equals 0, 2 steps of equal size, approximate h of 1. All right, well, let's do it. Right, so reminder about Euler's method, right, that formula that we have. Right, yn equals yn minus 1 plus dy dx evaluated at xn minus 1, yn minus 1 times h, the step value. Whenever you're doing Euler's method, I would highly recommend always just making yourself a little table, n, x, y. So 0, the initial condition, right, n equals 0 is just the starting value, starting point, which in this case, h of 0 equals 2. So, oops. If I plug in 0, I'll get 2. Let me shift this up so it's easier to go back and forth. All right, it wanted 2 steps. Right, 2 steps of equal size, okay? And my goal is to approximate h of 1. Right, so my end goal is that I end up at, got it, at 1. So to get from 0 to 1 in 2 equal size steps, so it should just be going by 1/2. Right, h is 1/2. Now, what are the y values? That's what we need to figure out. So let's do it. So let's first do y1. So that's y0 plus dy dx evaluated at x0, y0 times h, which we know is 1/2. y0 is 2. Okay, plus dy dx. So remember, our formula for dy dx was, I don't know why I said remember, because I don't remember, x squared minus 1/2 y. Okay, so you might have to do some side work. I don't know, maybe you can just do it in your head. So x squared, so 0 squared is 0, minus 1/2 times 2. Okay, so that would just be -1 times 1/2. So this is basically 2 minus 1/2, which is just 1 or 1/2, or 3/2. Now let's figure out y2. So that would just be y1 plus dy dx evaluated at x1, y1 times the step size, which is 1/2. y1 is 3/2 plus dy dx at x1, y1, so at 1/2, 3/2. All right, that's going to be more complicated. So x squared minus 1/2 y. Okay. So 1/2 squared minus 1/2 times y is 3/2. All right, keep in mind this 1/2 here is from my x1. This 1/2, that's the coefficient in front of the 3/2, is just from the original equation, that minus 1/2 up here. All right, all that times 1/2. One-half squared is 1/4 minus 3/4 times 1/2. 1/4 minus 3/4 would be -2/4. -2/4 is -1/2. So this is -1/2 times 1/2. So 3/2. -1/2 times 1/2 is -1/4. So minus 1/4. That would be 6/4 minus 1/4. Which is 5/4.